Hello and welcome back to the Hyperthesis episode 89. Today we're going to be talking a little bit more about some theory stuff that we find interesting. My name is Feely.
I'm Patrick.
And I'm Liam.
All right. So, in the last couple episodes, we got guests. So I think this one we got a little more relaxed, see, no pressure to. So
we
we're gonna
actually have to
discuss a
talk
bunch
about
of stuff.
this time.
Yeah, so we actually, have to read some stuff and, pick our brain a bit before we get to pick the guest brain, get them to tell us stuff. All right, so today for the intro topic, what do we have for today? So we have the super heavy element, the new look of it. All right, who wants to take it away?
Well, so super heavy elements have always been something that's interesting to me because it's kind of a nice mix of particle physics and chemistry and nuclear physics. And there's a lot of cool stuff that goes on with the creation of heavy elements. And so for heavy elements themselves, the first one that might come to mind is something like gold or silver or lead. But the heaviest stable element that's like naturally occurring is uranium. So uranium, which on the periodic table is, I believe, number 92. And I will just double check to make sure that's right. Yeah, it's number 92 with a atomic mass of 238. That one is the highest we can go in terms of mass, at least naturally. So we can't find like neptunium or plutonium naturally occurring beyond that.
Yeah, the funny thing where literally when I read the super heavy word, like the first thing that come to mind was uranium. It wasn't even gold because like gold to me, you look at the periodic table, it's not that heavy, right? And then that's not and when you say super heavy, so it's not just heavy. So it must be somewhere near like the limit of it. And also it depends too, right? The colloquial use of the word heavy kind of implies the weight. So I don't know what's the density of the uranium is. Even though each atom can weigh more, it doesn't mean it. Or if the material is not dense, it can be light still.
Yeah. So in this case, when we talk about heavy, we're talking about the atomic mass. And when we're talking about the heaviest abundant element, instead of just talking about the atomic mass itself, which is essentially just the addition of protons and neutrons within the nucleus of the atom, electrons don't really weigh too much, so we don't really include them. But in this case, when we talk about super heavy elements, we're just looking at the number of protons, also known as the atomic number, the Z value. And so if you look at a periodic table, I've linked one of my favorite interactive ones in the show notes below. You can see that we have up to number 118, which is oganesson, a noble element. But anything above uranium has been manufactured by people. So for example, plutonium, that's made through a certain type of enrichment process from uranium. And so this is something that was very commonly produced during the period of experimenting with new nuclear technology and, of course, the development of nuclear arms. But as we go higher and higher up the periodic table, as we get heavier and heavier in mass and then more protons, these elements become a lot harder to produce and detect, and they really don't last a long time at all. So, for example, uranium, it can have a half-life of many, many thousands of years for the most stable isotopes, but elements like oganesson or tennessine or any of the new ones that have been discovered, which actually was quite recent within the past few years, they really don't last a long time, from nanoseconds to seconds. So it's very hard to detect these, and we actually have to produce them in the first place. And so to produce heavy elements, it's not so much just bombarding other elements with neutrons or protons and seeing what happens, like how we discovered elements like plutonium and other ones that are closer to uranium, because as you do that, they become more and more unstable to the point where you actually need higher powers and higher energies to force those neutrons into the nucleus and make sure that you're actually producing them. So a very interesting paper came out recently with a related news article in phys.org saying that scientists actually discovered a promising way to create new super heavy elements. So ones which extend beyond our current knowledge of number 118. Now,
Do they smash them together and hope they stick?
Kind of, yeah.
That's how
That's how.
I feel like that's how you do things in physics, you know? They do that with particle colliders, and so if you want to make things heavier, you just throw them at a wall and hope they stick, maybe. I don't know.
Just to note, in particle colliders, you smash things but hope they break apart, whereas
Yeah,
here
yeah.
you'd smash things and you hope they stick together.
Yeah. The reverse.
So this specific research comes from the Lawrence Berkeley National Laboratory in California, and it was published in Physics Review Letters. We'll also link that down below. But it has to do with how we actually produce these super heavy elements. And now you might be asking, well, why do we need these super heavy elements if they don't really last a long time? They take a lot of energy and time to create. And that's a lot of things in physics. Why do we do any of it? For a lot of sciences too. But there's this idea within chemistry and within nuclear physics of the island of stability. I don't know if we've talked about it before on the show, but it's a very intriguing topic that essentially says once you reach a certain Z number or number of protons within a nucleus, they don't decay like the very radioactive elements do that we've created so far. And so this island of stability was first proposed to occur around atomic number 112. We haven't really seen that yet just because we haven't produced the elements at 112 or above in very large quantities at all. But there's this possibility that as you go to higher numbers of proton numbers, the radioactive decay that happens really diminishes and you have these very stable, super heavy elements.
Well, what's the reasoning behind island of stability? Is there a reason why? Because it seems like the structure inside nuclei are not exactly like crystals. Like crystalline structures, you can have a unit cell with many particles, right? Like you can have like a big crystal where it's stable, like the structure is rigid. Where I don't know about like what, or if we know the actual structure of the nucleus, and we know it has protons and neutrons, but it's not. We don't exactly know how they arrange inside, right? It seems to be like a quantum mechanical engagement there, that quantum binding, that like the strong force that hold it together, but there's no structure to it. So I'm curious as to what is the reasoning of that island of stability.
I don't know the answer to that, but I think when you think of atoms and nuclei and electrons, you have to think quantum mechanically. You can't think of it as like rigid, I guess. Like, the classical models you see in like high school and your undergraduate, like depending what scale you're looking at, you can do that. But I think when you're talking about decay, you really need quantum mechanics, and maybe you get like effective bound potentials, and half-life can be calculated from that. I don't remember how that works exactly.
You took a quantum field theory class, so you should know this with quantum chromodynamics, huh?
Yeah, I took not that. I was taught quantum field theory from particle physicists, not the chromodynamic guys, more of like the QED guys, the ones who are concerned with other things. But yeah, chromodynamics is pretty cool. QFT, changing number of particles, when your atom decays, that's considered a changing number of particles. So all that stuff's interesting. I wish I had more time to learn it.
Yeah, QCD is pretty cool, and you're exactly right. This is in the quantum realm, and more so the QFT realm. where much like an atom and the electrons orbiting it have certain arrangements. So there are certain shells that electrons fill. If you've ever seen like the simplified Lewis diagrams where the first shell is 2 and then we get more and more as you go out in shells. This same concept can be used to describe, not quite as accurately, but it can be used to describe shells within the nucleus as well.
Yeah, it can. And I remember learning about that. Like, you learn in high school that you learn about these SPDF orbitals. When you do chemistry, you're like, oh, there's all these quantum numbers. And your chemistry teachers are kind of like, these are the quantum numbers. Like, hydrogen is this one and helium's that one. And they just have these numbers and there's these rules in their periodic table. But all that comes from not quantum dynamics, quantum mechanics. So you derive that all by solving the Schrodinger equation, and at surface level it's the Schrodinger equation. But then you get into like decay and stuff. You need to do quantum field theory. But I remember thinking like learning all that and saying like, oh, that's so cool. Like, this is where all that stuff comes from. But when you learn it in high school, you learn about electron orbitals. So electrons orbiting around a nucleus, and you just kind of like say the nucleus is way bigger, so it's this kind of fixed thing that everything orbits around, like the planets around the sun. But protons and neutrons and the atoms that make up the nucleus, they have their own SPDF orbitals and their own kind of configurations, like you just said, their own probability distributions. So yeah, it's cool stuff.
Well, it's essentially the angular momentum, right? That's what's being described here. The quantum numbers, what's called, is this element of angular momentum. Oh, William might have something more to say about it, but I think in high school, what we learn is that like from it's almost we learn like the history of physics, or the physics to the lens of history, because we start from like, I don't know, the an atom is like a sphere, a ball, and then there's the plum pudding model, and there are all these stuff that come out, right? And I think a lot of common perception of an atom would be the nucleus in the middle and electrons orbiting around it. And then we're gonna get to the cloud thingy, right? Where you have the orbitals as like these balloons of bubbles and of probability. And you see this evolution's kind of intriguing.
Yeah, because I guess if you're teaching someone, you don't want to just start off with like, all right, here's quantum field theory. Like going through it historically, it's kind of like going through it intuitively. Like, it's as if it's a speed line process, like fast paced process of going through history. You're like, all right, like if I see an atom and I'm some scientist who knows nothing about it, like what's the first thing I'm gonna guess or the first thing I'm gonna think? And you're like, all right, maybe it's this plum pudding model or whatever. And then yeah, so the quantum numbers, like they come from solving the Schrodinger equation. Not all of them are angular momentum, but some of them are. But they're just it's really cool. I wish everybody could go through that, like go through it, all this chemistry in high school, then go do a physics degree and get an appreciation of where all this stuff even comes from. But it's not for everyone, and also it shouldn't be for everyone. If everyone was a physicist, the world would fall apart. But anyway, back to these heavy elements. We are
Yeah.
some physicists, so we can talk about it.
So with these heavy elements and going back to these kind of shells that they fill in its most simplest form, essentially there's what are known as magic numbers within atoms and their nuclei. And these magic numbers just relate to full shells. So again, like how electrons can fill their shells, so can protons and neutrons, and they actually have different shells just because they have different charges and they behave a bit differently. And so, for example, for protons, the magic numbers are 2, 8, 20, 28, 50, 82, and 126, which you don't need to know those, but just know that they relate to helium, oxygen, calcium, nickel, tin, lead, and a hypothetical unbihexium, because we haven't actually discovered element 126 yet, should it exist. But these different magic numbers and the stability of both protons and neutrons, which just add more mass and create isotopes within atoms, can be related to each other in what's known as a nuclei chart, which shows the number of protons and neutrons. And in these charts, they show kind of protons in the y-axis, neutrons in the z-axis, and then the color, or the third dimension, relates to how long the half-life of those nuclides are. And what's interesting is that when you do the theory behind it, you see that there's this island of stability as you go to higher neutron and proton numbers that exists where the half-life is expected to be significantly greater than the isotope surrounding it. So it creates this island of reduced, or increased half-life, where you have essentially these magic numbers being filled in both the protons and neutrons. And just to note that when you do fill both the proton and neutron shells, then it becomes a doubly magic number, which great wording on that. So going back to the research that was just done, traditional methods to find these super heavy elements, especially as we've gotten higher and higher into the 100s, it was to bombard calcium atoms with different elements. So calcium atoms are, especially the isotope calcium-48, has 20 protons and 28 neutrons, meaning that it has the magic number of both protons and neutrons. So it's doubly magic, meaning that it's quite stable. And so we can add more to that in a rather effective way to try and search for the existence of higher atomic numbers. So just for reference, calcium-48 has a half-life of about 60 billion years, which is decently large. So these reactions are known as hot fusion because they essentially slam heavy isotopes into calcium, such as titanium-50 or zinc-70, and that's how we're able to produce these very heavy elements up to oganesson, which was discovered from these reactions with calcium. But this has been more difficult to achieve just because calcium is quite stable, but still has a lower mass. So the new approach that this team, led by Gates, is instead of bombarding calcium, they're kind of switching away from that. So to try and really explore this island of stability and get up to high numbers like Z119 and Z is equal to 120, beams of titanium-50 would work best because of their cross-sections. I think we've talked about cross-sections before. We won't get too much into them, but you can hear more from our recent episode with Jean-Marie, where we were talking about particle cross-sections. But it's essentially the probability that a particle will interact with something, whether it be another particle or light or something like that. So to be able to probe these higher and higher Z numbers, they started investigating, for example, the production of livermorium, which has been discovered using this calcium method, but by beaming titanium-50 onto targets of plutonium-244. And so what they do is they use a cyclotron, which just spins the particles around while accelerating it at the Lawrence Berkeley National Lab. And they're actually able to pump in about 6 trillion titanium ions per second, and then bombard that into plutonium-244. I will just say Lawrence Berkeley is one of the few places where you can actually find a good amount of plutonium. Now, they were able to make a slew of measurements over a period of 22 days. Again, going back to our episode with Jean-Marie, the longer that you have an experiment running, the more you can refine a cross-section because the more chance of an interaction and what you're actually looking for is recorded. So they determined that they were able to define livermorium 290 a bit better and actually found that it had 2 different nuclear decay chains. So essentially by pumping up the mass and optimizing for the cross-section of an atom that's bombarding another atom, we are able to strive higher and produce more of these super heavy elements. And so the idea is that we can look at using heavier elements like titanium instead of calcium to really try and produce these super heavy elements. So it's a nice step into the right direction of super heavy elements. And there are about 110 isotopes that are classed as super heavy that we know about, but there are another 50 that are expected to be out there. And there is a possibility that we'll either prove the existence of this island of stability, or our models are wrong and we have to look at things again. So really interesting article. It's linked down there if you want to read it. And very cool stuff in nuclear and particle physics.
All right. Thank you, Patrick, for the intro topic. Well, we're going to move on to the main topic today, which is the Aharonov-Bohm effect and Berry phase. So I think I'm going to be talking a bit about the first one, the former. The latter, I think it's Liam's domain. Well,
I wouldn't call it my domain, but I hear a
out
lot
of
about it.
out of three of us, you know most is your domain.
All right.
To me, my fascination on Aharonov-Bohm effect came from, I think, reading about it somewhere, and I think watching something. It's been a while. I can't recall that well. Memories kind of go when you grow old. Well, the common perception, or my old perception, was that the things that affect nature has the what do you call it? Something that is zero, or have no magnitude shouldn't affect nature or shouldn't change things, right? If you want to, I don't know, move your box by 0 centimeters, the box doesn't move. So it stands to reason that to be able to affect physical things, you need some type of scale or some type of magnitude, be it force, be it some type of interactions, or anything has to have magnitude.
I guess like the classical way to think about it is like forces, right? Like, if I move a box, I have to push it. If I just stare at the box menacingly, it won't move. I have to like apply a force to it. So that's kind of like the intuition you'd have, and I think that comes in. That's why, like, I know you're going to talk about it soon, but that's why this Aharonov-Bohm effect was kind of like this very surprising result.
Yeah, it makes perfect sense, right? And everything in our experience in human history has told us that, and the evidence is quite obvious. But this experiment kind of changed the way we look at things like this, and what it means to be able to influence nature. Maybe what we measure, like the strength of the force, it might not be the only thing that determines the influence on nature or influence on the system you're looking at. So one of the what do you call it? One of the core experiments that kind of shows this, or think about the thought experiment. Everyone knows the double slit experiment, where you shine, you send in little particles small enough, hopefully, wave a particle into the two slits, and they kind of have the interference pattern. So it would be like a little stripes instead of two thin stripes. You're gonna have a multiple of them, and we can calculate the intensity of each stripe, basically. But the particle can act either as a particle or waves, and those things can be changed upon observation. So that's one of the things that we discovered early on, which has become one of the foundation of quantum mechanics. The Schrodinger's cat was an analogy try to basically describe that type of nature. So it would stand to reason that if you observe the particle, it acts like a particle. But if you leave it alone, it will act like a wave if it's small enough. Like you shoot a beam of electrons, for example. So, well, it begs the question: what is exactly observation? And one thing that Aharonov-Bohm effect does is that, well, if you're gonna have the interference pattern on this slit experiment, and if you put something in between, like a little wire, and it have a little wire had a current in it, so it would have magnetic field around it, so it should affect the particles that are going through. In this case, would be electrons that are going through. So when that happens, this electron should behave like a particle, and we would not see this interference pattern. Makes sense. Great. But what if we isolate that wire, make it a solenoid, which is like a curl. What do you call it? Like it's like a helix. It's not a helix. It's like a coil, right? Like a
It's
spring coil.
it's like you have a
Yeah,
like you have a broomstick and you wrap a wire around it all the way up. It makes like this coil, like a
Yeah,
yeah
like a spring.
Yeah, helix.
yeah.
Exactly. So yeah, a helix, and it turned out in those shape, the magnetic field outside is cancel out. It's supposed to be zero. So there's no strength at all in for the magnetic field. So it shouldn't affect anything, right? So you should be able to do that. Or you can put some type of insulator that basically dam out all the magnetic field. So it from the outside will have no magnetic field at all, like zero. But it turned out even when the magnetic field is zero, it's still affecting the system. So what does that mean? Like because now even the magnitude of the magnetic field is zero, how can it affect the system? And it brings about the new way to look at the nature of influence in terms of instead of maybe the strength of it, the fact that the field or some underlying structures of nature exist just because something is being there is more important than the strength of the magnetic field.
So you're saying you have a coil of wire, and inside of it, yeah. So when you have a coil of wire, there's a magnetic field inside of it, but outside of it, there's none. And if you like shoot an electron past this coil, so it's still outside of it, it shouldn't. I mean, electrons interact with electromagnetic fields, but because there's no electromagnetic field outside of the coil, the electron should just go through unfazed. Um, but what I guess the Aharonov-Bohm effect is what they found is like, yeah, there actually is some effect from the coil, even though no electromagnetic fields interacted with the electron. Is that what you're saying?
Yeah, so if you, it's hard to show it without a diagram, right? Like so basically, if you shoot the electron onto a screen, a beam electron, you just should see like a circle, right? Like or
Mm-hmm.
just no interference pattern. But
Oh,
somehow
right.
when you put this thing in the way,
In the middle.
even though it should not affect the beam of electron, it does. Even though physically the magnetic field around it should be zero. So how is the magnetic field zero affecting the electron beam? And
Yeah, and that's why this is so shocking, right? Because you're like, well, no, we haven't done any. Like, there's no force acting on the electron, but somehow it knows about this coil. Very weird.
yeah, it's so weird. And as like, what is exactly doing that, right? And it turns out people explain it with the flux. The fact that inside the solenoid there's a flux of magnetic field. Flux is basically how you describe it. Like it's force per area or so, or like electrons per area is an yeah. It's like electric pressure per se, right? Like flux, but it has something flow through it. It's like a way to count a vector. Anyways, the fact that there's a flux, it produced like a phase change around it too. So what's affecting is not the strength of magnetic field, it's the phase change. So something is affecting it, but it's not the magnitude of the magnetic field.
The way I was taught this is, you know how you have like electromagnetic potentials, right? So in electromagnetism, you have electric fields, which are the things that you feel. Like if I held two magnets near each other, they push each other apart, and that's because they're pushing on each other. Well, there's electromagnetic fields interacting, and they cause a force that pushes them apart. But you can do this mathematical kind of trick where you can I don't hard to talk about without getting into calculus and stuff, right? But instead of talking about fields, you can talk about energy. So you can say that there's this associated electromagnetic energy, which you call an electromagnetic potential. And it's not a vector, it's a scalar, so it means it doesn't have like a direction. It doesn't point anywhere, it's just some function. And you can do the math of electromagnetism through those potentials. And often it's easier to do so because they're not vectors. You don't have to worry about 3 dimensions. You only have to worry about one. So I think the way to think it, like, somehow the Aharonov-Bohm effect is that even though there's no electromagnetic field outside of the solenoid, there's a potential. And originally people thought potentials were just kind of mathematical trickery. They thought it was like just some mathematical tool you could use. But it turns out that this experiment kind of tells you that there might be something more going on with potentials, because even though there's no electromagnetic field out there, there's a potential. So somehow maybe the potential is doing something that a field can't. That's like maybe there's something slightly wrong in there. I don't think so, but that's kind of like my understanding of the Aharonov-Bohm effect, is that there's potential, but there's no electromagnetic field. So that tells you something.
Yeah, it's the physical realization of the vector potential, right, in a more specific term. Because in electromagnetic theory, we learned that there's this something called vector potential, which is I
Oh
think
yeah,
which is
sorry.
represented by the A, the A thing,
Yeah, I
and
was talking about like a scalar potential for electric fields, but magnetic fields have a vector potential.
yeah, it's weird because all our life we have learned that potential is this scalar thing, and then we go to learn E&M. We're like, well, there's something called vector potential. Like, excuse me, did you just put vector and potential together? Yes. And you learn calculus, we realize that, oh, we do the curl bit and we get like the magnetic field, right? Like, okay, so it's kind of neat because usually you take the gradient of a potential and you get a force, right? That's how almost all forces work, including the electric force. And curl V, you get the E, right? Not curl, sorry, the gradient of V, and also and a lot of auto potentials too, like gravitational and stuff that we learn in undergraduate physics or high school physics. It turned out for the magnetic field, we need something called a vector potential, and which is a vector. And so in this case, well, there is some kind of physical realization of this kind of vector potential that maybe is there even before the strength of the magnetic field. Maybe the strength or the magnitude of the magnetic field is just one component of the physical reality that we measure, but it's not the only thing that affecting nature of it. The one thing I want to point out too, I think this is kind of, um, to me, it feels like, or feels sounds weird. It appears like it in a different category of influence on nature. Because when you use force, there is the magnitude, and there's maybe sometimes, most of the time, have direction to it, right? But and in this case, it's more like an observation effect, which are not totally understood. Like the quantum mechanics tells us how the wave function evolved. Whatever wave function means, it's very well defined. Something that particle has this wave function that governs it. Basically, to tell you almost everything about it quantum mechanically is encoded within this wave function. And quantum mechanics is a theory of about how this wave function evolves and interact and deal with these, with Schrodinger's equation, and be it relativistic or not, this is the entire big theory. But it never explain how wave function collapses. It just says it collapses, right? So I think this is on the category of the outside. So like how how this electron wave function collapse when you have this type of the vector potential in there, which I think this is the area that's outside, a little bit outside or on the edge of quantum mechanics.
Yeah, like wave function collapse is a big area of research. Actually, people want to know what that even means, and they want to know what a wave function is, because like it has a really good statistical interpretation, but not so much physical interpretation. And that's kind of the whole point of Schrodinger's cat. the whole Schrodinger's cat thought experiment is basically just pointing out how absurd quantum mechanics sounds at classical levels. It's on macroscopic scales, it makes no sense. Your cat can't actually be both alive and dead at macroscopic scales. But on microscopic, scales, maybe it could.
Yeah, well, it begs the question, right? If the or whether the wave function is a mathematical trick or is it a physical reality or it's like a physical quantity. It's kind of strange, and we could say the same thing about. I like to say this all the time. That I believe time is a trick. It's not. It's not a physical thing. But it's another whole debate, right? And I think it's going beyond the scope of the physical, experimental, provable thing that or like experiments. Because how are we gonna find wave function? But since we kind of find like this, realization of vector potential, that we kind of be able to tell or infer that the vector potential is real in a sense that now we can see it happening this way. Maybe wave function in by the same manner or in the same type of argument, we could say, well, because we all these see all these quantum mechanical effects that follows the Schrodinger's equation, it seems to be governed by this wave function. So, and thus, wave functions are physical.
Yeah, well, like for the Aharonov-Bohm effect, right? Like you see physically the pattern on the other side, that interference pattern. And same with like just the regular double slit experiment. You can't describe that without a wave function. The wave function tells you the probability to find particles where they are, and then when you take many, many experiments, you see the probability matches it. So it's like I think wave functions are physical in some sense because they give you what matches reality using probability. But yeah, then that's a whole lot debate, right? Like what are they? They're not like a real thing, but they give you real things. I don't know. But yeah, the Aharonov-Bohm effect is definitely real because Aharonov and Bohm. I guess I don't know the history of that. Like, did they both work on that together, or was it like someone proposed it and one of them did the experiment? I don't quite know. Maybe we'll learn about that later. But
Well, so but what does this have anything to do with the Berry phase?
yeah, so so that I have a very long explanation for that, and I can start now. So, turns out that this Aharonov-Bohm effect, it can be interpreted as this thing called a Berry phase. So, what is a Berry phase? To understand that, I need to talk about um, adiabatic approximations. So, adiabatic in the context of physics, I found this good explanation that I liked in this textbook called Introduction to Quantum Mechanics by David Griffith. And that's like a really standard introduction to quantum mechanics textbook. Like all three of us here, when we took quantum mechanics as undergrads, we used Griffiths, I think, right? Yep, we did. So in this book, they talk about the Berry phase, and so in adiabatic approximations. So what I say is a lot of it's coming from that. So first, imagine you have a pendulum. It's a ball on a string, and it swings back and forth, right? Like you're sitting on a swing and you swing back and forth, or like the pendulum in a grandfather clock. But now imagine that the pivot point from which it swings, like the top of it where the string is hooked onto, imagine that oscillates back and forth. Imagine you can oscillate that back and forth. And if you do it really, really aggressively, then the pendulum will begin to swing chaotically with chaotic motion, which we actually talked about a little bit in the last episode in the context of three body problems. But in the context of a pendulum, it'll oscillate chaotically if you oscillate its pivot point very fast. But imagine you oscillate the pivot point of the pendulum, the point from where it swings, very, very slowly. You do it slowly enough that the pendulum it doesn't really notice that it's actually that its pivot's point changing. So it'll just continue to swing back and forth as if nothing's going on. That's what we mean by an adiabatic process. The gradual change of some external condition of a system, so that it doesn't really notice it's changing in some sense.
I think okay, because maybe I'm coming it from the thermodynamic point of view, because it's
Hmm.
basically the same definition explained differently.
Yeah, I
Because
think
in
so.
thermodynamics, it means there's no heat exchange between the system and the environment or outside of it. So if you think of it that way, if your system is the pendulum, right, and the environment is the rest, and by moving the pivot point, you are adding the energy into the system. So there is the heat exchange that coming into the pendulum. Heat, in this case,
Hmm.
mean the kinetic energy that's be coming to it. And when you slow down the movement of the pivot point enough, so that it's so slow that the system doesn't feel its effect at all. It's like there's no heat is coming in, and that's what happened in a thermodynamic system. And you have a box and you insulate it from the world outside, right? Like, but there's no perfect. It's not nothing is perfect insulator, right? So it always be a tiny bit of heat exchange, but if that heat exchange is small enough, so the process is adiabatic. So it seems like there's no heat exchange at all, right? In the apparent sense. So in this case, in your case is more like the kinetic energy, and in the thermodynamics and statmech world is more like just heat. Or in a sense, some people would argue heat is kinetic energy too, but yes, there's no exchange of energy or heat.
Yeah, there's different ways you can think about it, but it's you're changing some parameters slowly enough so that kind of your system. It's a like I know
It's
how to explain
isolated.
it. Yeah, like one way to think of it is in terms of quantum mechanics. So in quantum mechanics, adiabatic approximations are useful in a whole number of situations. Because again, it turns out doing math is hard, so a lot of the time you can approximate things to be adiabatic so that things are simpler. Like so, a popular example is in molecular physics. When you're doing these calculations of electronic structure, a lot of the time you assume that the nucleus of your atom. So we talked about atoms today a little bit, which was nice. You have your nucleus made of protons and neutrons, and you have electrons moving around them. You kind of approximate that your nucleus is just sitting there stationary, right? And the electrons move around it. But it turns out that's not entirely true. It's an approximation. The nucleus of an atom kind of jiggles around and vibrates and oscillates with its own kind of characteristic frequency. But the electrons move much faster than the nucleus does because the nucleus is way heavier than the electrons. So you can approximate that the nucleus oscillates back and forth very, very slowly, adiabatically, like this pendulum example. Like the top of the pendulum oscillates very slowly while the bottom moves quite fast relative to it. You can do this thing in molecular physics, and it's called the Born-Oppenheimer approximation. Actually, something Oppenheimer, one of these things that's not a nuclear bomb that Oppenheimer is known for. So that's an approximation they use in molecular physics, or at least they did at one point. I'm not sure how popular it is now. I don't really do that kind of stuff, but I'm sure it still comes up. Um, so one way to think of it, maybe this isn't as useful for people who've never heard of this, but for people who know a little bit of quantum mechanics, imagine you have a particle in a box. Um, its ground state wave function is given by like a lump, like half of a sine curve. If you've seen that before, goes to zero at the boundaries and it kind of peaks in the middle. If you begin expanding the width of your box, if you suddenly double the size of your box, then your wave function is only suddenly half the size of the box, and then it kind of expands and fills out the rest of the box. But if you vary the length of the box very, very, very slowly, then the sine wave itself, the probability to find your ground state particle in the box, it'll expand with the box itself, and it won't change suddenly. It won't have this sudden abrupt change in it. It changes adiabatically. So that's kind of like a quantum mechanical example.
Yeah, I feel like you just Fourier transform your explanation, right? Because you just go from the space domain into the frequency domain, and that's one thing that is also adiabatic too, right? Like instead of, let's say, if something changed 10 times a second, and you want to be able to measure that consistently, and there's some noise, but if that noise is about 1 time every 5 minutes, right? So and if it's that slow and so it's not affecting your measurement that much. So basically, that's what kind of happened, right? Like if instead of like it looks like this heat and energy come in this frequency, but if the frequency difference is on the order of magnitude is acceptable, we can pretend it doesn't exist.
Hmm. So yeah, so if you have like a quantum mechanical system, and you're changing it in some way, you're changing it in time, you're not conserving energy. If you're changing something in time, like if I'm oscillating the top of this pendulum, I'm adding energy to it. So you're not conserving energy when you do these adiabatic processes because something is time dependent. Like the electrons orbiting this kind of relatively slowly moving nucleus. What ends up happening is that your wave function that describes the probability of where to find the electron, it or in some other system, the wave function it acquires these extra two phase factors. These yeah, one is a time dependent phase factor and one's a kind of um path dependent phase factor. So the first phase factor, phase is so just quick note on phase. Phase is this property that waves have. It determines the position of a wave in its cycle at a given point in time relative to some fixed point. Um, so when you think of a wave, think of a sine wave. It has like these peaks and troughs, and relative to some point, you can shift it a little bit, and you'd say that's like a phase shift. So phase is this really important concept in wave physics because it tells you information about the position and behavior of waves at given instances in time, and it tells you about how waves interact with other things or with each other through interference effects.
Oh, the way I like to explain it is through like the unit circle because that's what the sine and cosine really is, right? Or some people would argue is exponential stuff. But if you pick a position on the unit circle, you can have the angle of compared to like the zero axis or the x axis, right? And that's one mathematical way to describe phase. If you want to know where you are on the unit circle, you can either give them the x and y coordinate, which is x and y are basically sine and cosine, right? Or is it vice versa? But x, y, the coordinates are y and cosine, but you can also give them the angle, theta, and it's like you know exactly where you are. But the good thing about phase is that 360 degree or 2 pi radians, you're gonna end up at the same place. So that's why it's periodic. You can describe where you are using sine or cosine, or you can describe where you are using the phase.
Well, that's the interesting thing. So the Berry phase doesn't do that, which I'll describe. So so whenever you're doing these adiabatic things, you get these two extra phase factors in your kind of wave function for your quantum mechanical system. You get this dynamical phase factor, which is kind of due to the time dependence of your energy, so the fact it's non-conserved, and you get a geometric phase, which depends on the path you take. So in the Aharonov-Bohm effect, it's like the electron that goes around the solenoid without ever touching any magnetic fields. The path it takes determines that can be understood that's what kind of comes into play when we're talking about this, which I'll get to. So this geometric phase factor, the second phase factor, that's path dependent, depends on the trajectory you take. It's also called a Berry phase, named after Michael Berry, who popularized this idea, and that's kind of what him and Aharonov are famous for. Aharonov-Bohm came up with this crazy experiment and said maybe the potential means something, not just fields. And Michael Berry came around and said, turns out you can think of this as a geometric phase, which we now call Berry phase. And I always like this because Michael Berry, I mean, I say this like every time his name's brought up, but he's like my grand supervisor. He was my supervisor. So, I'm always hoping for nice Berry phase discoveries because I can just be like, oh, the guy who discovered that was like my grandfather. Um, anyway, so with the pendulum example I gave before, right? Imagine you have a pendulum swinging and the top of it oscillates a little bit. Or just imagine you have a pendulum swinging and it's I don't know, it's in Toronto, like kind of close to where I am, right? Um, and it's doing this weird oscillation where the pivot point oscillates. And now imagine you're kind of like you're in space looking at Earth. You're looking at the Earth as it rotates. You'll see that Toronto does like a full closed circle orbit of the Earth. The Earth spins, and eventually, after 24 hours, Toronto comes back to pretty much where it was the day before, except because you're floating outside in space, you see that it's shifted a little bit. The 2D plane that the pendulum was originally oscillating in is no longer the same 2D plane from your point of view. And this is a little conceptually difficult to picture. It's really nice when you have pictures in front of you to look at. But the idea is that there's the pendulum's no longer where it was the day before. It's now got this slight angle off shift. And this is an example of a faux. Oh god, I don't even know how to say that. I always call it Floquet pendulum, but that's not right because Floquet is some other guy. It's a Foucault. Foucault? It's this very large pendulum. Physicists know what I'm talking about.
Foucault.
Foucault, okay. Yeah, it's an example of a Foucault pendulum. It's a very large pendulum, and that's an example of adiabatic transport around a closed loop. The pendulum's oscillating, but it's moving very slowly around the Earth, and it comes back to its original position. And that's non-holonomic. And what that means is that the state of the system is not the same as it was after a full rotation. So, like you were saying, phases, you start somewhere, you do a full rotation, you come back, it's the exact same. You can have non-holonomic phases, and Foucault pendulum's an example of one. So you return to your same position, and your state's different a little bit. And the Berry phase in quantum mechanics is an exact example of a non-holonomic phase. When a quantum state is adiabatically allowed to vary and complete a rotation around some closed path, it no longer is in its original state due to this kind of extra geometric / Berry phase factor it obtains. And this is where, coming back to the Aharonov-Bohm effect, Berry pointed out in his famous paper, I don't remember what it's called or where it's located, I can find that maybe. But this is why it's called the Berry phases paper, that you can actually view the Aharonov-Bohm effect as an example as a geometric phase, or a Berry phase. The wave function of the quantum state, it passes around, it does a half loop around the solenoid, and then because interference effects, it's like it does a half loop on one side and a half loop on the other side, so you can treat it as a full loop. Even though it's not interacting with any magnetic field, quantum mechanically it picks up a Berry phase factor due to this trajectory and its interaction with the electromagnetic potentials. And that the factor you get, this phase factor, directly explains why you see this kind of interference effect.
Okay. This reminds me of do you remember magnetic hysteresis, right? Because you will have the well, you don't end up where you start because this type of hysteresis, but that's not the Berry phase, right? Because that's not the. Is that the non-holonomic stuff you're talking about too? Is an example of it too, or is just a special case? Because well, hysteresis, I mean, is quite explained, right? Like in the magnetic domain, but I'm not sure what you mean by, because when it's not end up at the same place or on the same state, how can you say it has done the total revolution if it's not at the same state?
It's non-holonomic. It's holonomic and non-holonomic. I think it's all about topology and things like that. So when you talk about hysteresis, there might be some way to map it to some topological viewpoint. But yeah, the idea is that I don't fully get it. Like the classical pendulum, the Foucault pendulum example is that if you're looking at the Earth from far away, it's done a full rotation from the Earth's point of view, but from your point of view, it's kind of shifted a little bit. So you got to be careful with how you think about it, I think. But in quantum mechanics, it's like you can do a full loop of a system. So you can do a full 2π circle around something, and you get this extra phase factor because quantum mechanics is weird.
Yeah, isn't that a matter? If you say topology, it seems to me it is a matter of change of observer. Because
I don't think that the example with the Foucault pendulum, I think.
Yeah, it is, right? Because if I just look at a pendulum and not Earth, I'm gonna get exact same state back because that's the point of periodic behavior. Yeah. But if you look from the outside, it's not gonna end in the same place because it's the pendulum is on the Earth, but it doesn't mean it. So if I am to describe the pendulum just in the box on the reference frame of just the pendulum, it would not pick up any extra phase. But if I am to pick up from the reference frame of pendulum plus Earth is gonna have the extra phase.
Yeah, and phase is a very weird thing. There's actually I want to get Josh to come back and talk about that. I don't know if he did in his episode. Phase is like it's not quantum observables are weird. You can measure phase, but it has no operator, no Hermitian operator, right? So there's phase is a very strange thing, and it's to do with the weirdness of like waves and things like that. But I think like I gave that example. Foucault pendulum is like it's a non-inertial thing, um, and in quantum mechanics, like it's not really about your viewpoint. In quantum mechanics, it can definitely just happen. Things can pass around full loops and get this extra phase factor.
So just as I guess a different visualization than a Foucault pendulum is, let's pretend you had like an arrow, or like one of those signboards that was, you start at the equator, it's pointing west, and then you um, essentially just walk north, um, towards the North Pole, keeping the sign oriented. So you're always facing in the same direction. Um, and so you're walking with this arrow that initially starts to point west, but eventually it will point south. And then uh, let's say you go up around like the prime meridian, and then you go 90 degrees out from that, and then start to go down back to the equator, and then walk all the way back to where you started from. If you look at exactly where that sign is pointing or where that arrow is pointing, it will actually shifted even though you're back to the same place. So you can kind of approximate that triangle that you make on the surface of the Earth. You can make a circle on the surface of the Earth. But just because of the geometry and the way in which you've maintained orientation, um, or not maintained orientation, I say, by going along the surface of the Earth, keeping the orientation of that arrow the same, but by essentially switching where you are on the surface, you can make a full rotation, if you will, on the 2D surface of the Earth. But the direction of that arrow will have shifted by, I think it's like 90 degrees, which is the offset that you have when you switch to the North Pole. But meanwhile, you haven't really changed directions purposely. You've been careful to keep it pointing in the same direction. So that's a kind of, I guess, fun way to visualize the Berry phase. And you can do that at home, especially if you have a globe, of just like tracing your finger along and then taking it down and seeing how that direction changes as you make that loop on the surface of a globe.
Yeah, that's probably a way better way to visualize it than I do. And that's like you get these Berry phases in like all kinds of quantum mechanical situations, like topological insulators, the quantum Hall effect, which is something maybe we should talk about if we haven't before. But it shows up whenever you're like kind of tracing some particle or some trajectory in your system over some surface or some path, and it's interesting. So the Aharonov-Bohm effect, the take home message is that it's an example of a Berry phase, and I'm not 100% sure where the adiabaticity comes into that. It might be like a non-adiabatic version of the Berry phase. I can't quite remember. There might. I genuinely don't remember.
I thought
I hear.
adiabatic just makes the system describable, because if you're not gonna make it adiabatic, like you're gonna have to consider external factors which are annoying.
Yeah, I think it's more so that it's able to return to its initial state in some way. And think back to like thermodynamics, where you have an adiabatic engine. There's no presence of hysteresis from external forces, where there's a shift up or down, or net loss and energy. Things happen, at least in thermodynamics cases, slowly enough that there is no energy that's lost, and so it's able to return to its exact same state. But in this case, it's able to return to exact same state in some parameters, but not others.
Yeah, the energy is actually directly affected by the magnetic field inside the solenoid, even though there's no magnetic field outside, or the magnetic potential inside the solenoid.
Oh, I thought they would
Even
say
though,
magnetic flux inside the solenoid.
yeah, there's different. There's so many ways to look at it. But there's no doubt that this was a really important experiment. Every year, I hope for someone to win a Nobel Prize in this field, because I think Aharonov Aharonov and Bohm are both not with us anymore, I believe. Um, and Michael Berry's still with us, but they don't like giving out Nobel Prizes to groups of people where they don't give them to dead people, for one thing, for whatever reason.
Well, I
And
mean, if
they
they
like,
showed up to the ceremony, that would be, a great discovery, isn't it?
yeah, true, we would discover ghosts. Honestly, if I knew that if I died and then figured out that they were going to give me a Nobel Prize but didn't because I was dead, I might come back to life for that.
Well, all right. I think we had a great and fruitful discussions about the Aharonov-Bohm effect and Berry phase. I think this episode is a little bit theoretical heavy, but it's like taking a break from the great topics of the guests, right? We're gonna go to heavies into the physics a bit, which is quite fun. All right. So before we head on to the story, we're gonna get Patrick to tell us about how to reach us and such, and then the story.
Absolutely. So today we delved into a decently complex topic, which is hard to describe, especially without pictures. So if you have questions for us or comments on what you would like to hear, or if you would like to be a guest on a future episode, we would love to hear from you. You can reach us a few different ways. The first being our email. You can find us hyperthesispodcast@gmail.com, where you can send us an email. We are pretty good to check that consistently. You can also make suggestions for episodes if you're just dying to learn about a topic, anywhere in science. We are more than happy to discuss it. It doesn't have to be physics. I mean, I'm no longer study physics, so we like all walks of science and hearing about the research or whatever your field of study might be interested in.
Yeah, come advertise your research. It's a easy way to do that too.
We also love to have young scientists on, whether you're a grad student or a young professor just starting out. We would love to bring people into the show. If you are, I guess, hip with the times, we'll call it, and you have an Instagram account, you can send us a DM. We are at the Hyperthesis on Instagram. We also post updates of when we are posting episodes, as well as some other fun pictures. I think a picture that was posted there not too long ago was when all three of us met for the first time in like 4 years to watch the North American solar eclipse of 2024, which was an exciting time. Now, if you're listening to us, congratulations, you found us one way or another. If you found us on Spotify, that's where we're based out of, but we are on pretty much whatever podcasting service is available, whether it's Apple Podcasts, YouTube Music, Audible, or wherever you get your podcasts. We are also on YouTube. We'll see how Catch Up with Season 7 goes by the time you're hearing this, but we're very excited to have that avenue opened up as well. So you can share us with your friends, whether on YouTube or whatever podcasting service, especially if you know they'll be interested in this topic. Although have heard a couple people say that they also like to listen to us while driving or while working in a lab. So lots of places you can give us a listen. So make sure to reach out to us in whatever way you prefer. Give us a listen, give us a share, and if you can, give us a rate or a subscribe, download our episodes, whatever that means. So thanks for listening, and feel free to reach out to us, especially if you'd like to be a guest. So for today's story, leading right into that, I'll try and be a bit quick about it, but it's actually decently hard to be quick about our main topic today, which is David Bohm. So as we heard from this main topic, there seems to be a lot of concepts named after Bohm, including the Aharonov-Bohm effect, but really he was quite instrumental in a lot of developments within quantum mechanics, which we'll get into more later. Now, we've also discussed in the past Bohmian mechanics, also known as the de Broglie-Bohm theory, or more commonly, the pilot wave theory. This is a really interesting theory that is an alternative to what's generally taught in quantum mechanics, but it's still existent today, partly because there's validity to it, and partly because Bohm was a very well-regarded physicist in the 20th century. He had many ideas that went against what was commonly accepted, and along with being a notable physicist, Bohm also delved into neuropsychology and philosophy, especially philosophy of the mind. He explored how the mind relates to the body and the world, and I guess with all this as a nice teaser, let's spend a little time talking and getting to know David Bohm. So Bohm began his life in the state of Pennsylvania in the United States of America as the son of Samuel Bohm, a Hungarian Jewish immigrant, and a Lithuanian Jewish mother, Frida Bohm. He was born on December 20th, 1917, so shortly before the end of World War I, in the town of Wilkes-Barre. Apologies if I mispronounce that. I'm assuming it's anglicized. He was mostly raised by his father, who owned a furniture store, and was also the assistant to a local rabbi. So he did have some religious upbringing as well. But despite this, he quickly became agnostic before he even attended post-secondary schooling. For his undergraduate, he attended Pennsylvania State College, which is now known as Penn State University. He also did not want to run a furniture store, so he became more and more fascinated with studying physics. At Penn State, or at the time, Pennsylvania State College, and against his family wishes, he completed his bachelor's degree in physics in 1939 before moving west to further his education. Now, a little bit of a spoiler, for those of you who have seen the movie Oppenheimer, you may have heard Bohm's name a few times, and he did study a graduate degree in physics at Caltech, or the California Institute of Technology, where he spent a year before moving on to the theoretical physics group at Berkeley, California, joining Robert Oppenheimer, and that's where he pursued his PhD. Now, there were a lot of big names around Bohm at that time, including Oppenheimer, and based on the fact that Oppenheimer was heavily involved with the Manhattan Project, you might assume that Bohm was as well. However, for associations with being a member of with members of the communist-leaning political groups, not even being a member himself, Bohm was not given clearance by the project director of the Manhattan Project, Brigadier General Leslie Groves, to join when it began in 1942. So Oppenheimer wanted him there, especially since he was his PhD student, but he was refused security clearance. Instead, Bohm taught and focused on plasma, synchrotrons, and syncocyclotrons, which are different types of particles, accelerators, which we touched on earlier, along with theoretical calculations describing collisions between protons and deuterons, which are heavy elements of hydrogen, mainly with a neutron added in there. So these equations, especially relating to particle acceleration and collisions between protons and deuterons, were very useful in the Manhattan Project, as you might imagine. And so his work actually became classified right away, to the point where even though he was not involved in the Manhattan Project, he did not have the proper security clearance to work on anything related to his own work. So as soon as he wrote it, it was classified and he wasn't able to see it. Because of these very complicated intricacies, he received his PhD in 1943 through a certification from Oppenheimer that he had successfully completed his research, because he couldn't write or present about his results. So his thesis doesn't exist because it was classified at the time. Now, after finishing his doctoral degree, he stayed as a postgraduate at Berkeley, working on the theories of plasma, which eventually led to his discovery of Bohm diffusion in electrons, which I don't know if we've talked about, but if we haven't, it's really quite fascinating. But just very briefly, this described a way in which plasmas diffuse across a magnetic field, and it's linearly dependent on temperature and inversely linearly dependent with the strength of the magnetic field, which is a lot higher diffusion rate than previously thought with just a random walk. Now, during this time, the war was still ongoing. Bohm still did theoretical calculations for mass spectrometers found at the Y12 facility in Oak Ridge, Tennessee. Now, again, if you've seen Oppenheimer or if you're familiar with the Manhattan Project, you might recognize that name as a place where uranium was enriched for the first atomic bombs. And he may truly be one of the people most involved with the Manhattan Project without actually being a part of it. Now, unfortunately, suspicions for association with communism continued after the war, much like Oppenheimer's, and although he became a assistant professor at Princeton University in 1947, there was actually a lot of distrust from the university, which inevitably led to his suspension. During his time there, he did work with Albert Einstein, but his refusal to testify during a period of McCarthyism, and also some run-ins with the Princeton president, even though he had the support of Einstein, meant that he had to leave the country and ended up at the University of Sao Paulo in Brazil, There he became a professor with the recommendation of Oppenheimer and Einstein, which it's hard to think of a better recommendation than those two. I can't imagine the letter they wrote. Or they just said, let this guy in, and boom, done. Now, around this time, Bohm published his first book titled Quantum Theory in 1951, but he decided to go against the kind of more so orthodox interpretations of quantum mechanics. This work started with WKB approximations and the fact that led to deterministic equations. He disagreed that an approximation could convert probability theory into something deterministic, so he set out to explore different interpretations of quantum mechanics. And here, pilot wave theory was born. This is also known as a hidden variable theory, among other names, which we discussed earlier. But this theory actually eventually led to John Bell developing the Bell inequality, which rules out local hidden variables, but is still something that's actively researched today, as Liam has talked about before.
It's also called Bohmian mechanics after him.
Indeed. But going back away from Bohmian mechanics and the pilot wave theory to his personal life, upon arriving in Brazil, his passport for America was actually confiscated by the American consul, and he could only use it to return to America. This encouraged Bohm to pursue a Brazilian citizenship, which he received, and therefore had to sacrifice his citizenship with the US, which means that the US lost a fantastic physicist. During his time in Brazil, he worked with many people to further his research in causal theory. But again, his theory was met with a lot of skepticism, as many physicists followed and still follow the Copenhagen interpretation. Now, this was all done over the span of about 4 years before Bohm moved to Israel. There he met his wife, Sarah Wolfson, whom he married in 1956, and he also met Yakir Aharonov, and together they pushed results that we discussed today with the Aharonov-Bohm effect. Now, following his work in Israel, Bohm relocated to Bristol in the UK in 1957 as a research fellow at the University of Bristol. Here, he was made a professor of theoretical physics at London's Birkbeck College, where he stayed for the rest of his career. Now, aside from physics, Bohm had many interests, including exploring the nature of consciousness, especially how thoughts relate to attention, motivation, and conflict. It's thought that these ideas began with Bohm's interest in Marxist ideologies and Hegelian philosophy. His interests led him to correspond with Jiddu Krishnamurti, a philosopher, and they actually made recordings from their dialogues, which were eventually published in several volumes. He delved deep into the impact of individual thoughts and their interactions with society, and one of these themes was the cause of solutions to problems, but caused all of those problems in the first place, which we won't get too much into that. Maybe we can have a discussion episode one day to discuss Bohm stuff. But he likened this kind of thought process to getting more sick by going to a doctor. Now, I won't get much more into his philosophical teachings, but he did pursue this area of interest in philosophy for much of his life. After he retired in 1987, good for him retiring from a faculty position. We need more of those people. Bohm still continued with his work in quantum physics. He traveled the world speaking on both physics and philosophy, and even met the Dalai Lama. He was elected to as a fellow of the Royal Society, but unfortunately suffered from reoccurring depression and was admitted in hospital in the spring of 1991. He did receive treatment, but ended up having a life-ending heart attack in London on October 27th, 1992, at the age of 74 years old. His last work was published posthumously in collaboration with Basil Hilly on quantum theory. Now, Bohm leaves behind quite the legacy, much like in our last episode, but more so of renown and controversy, with a film titled Infinite Potential based on his life and a book of the same name as his biography.
I don't know if this is true, but I imagine that you said he went to Bristol, and University of Bristol is where Michael Berry spent his whole career pretty much, right? So I imagine they met and talked, and that might have helped motivate Michael Berry to do Berry phase things for the Aharonov-Bohm effect.
Yeah, I imagine that's absolutely the case. I mean, they were alive at the same time, and although Bohm died in 1992, his contributions to quantum mechanics, whether it's through the people, like possibly meeting Barry and the work that's done by people like Barry and so on, have led to a lot of breakthroughs. And his completely alternate theory to quantum mechanics still survives to this day and is still being considered. He truly led quite the remarkable life, moving between many different countries and facing criticism and controversy, while still being involved with one of the most top secret projects in the world. But he was troubled, unfortunately, and suffered because of that. Now, although his legacy is still felt today in the name of things, maybe one day we will be able to find agreements with the pilot wave theory over the Copenhagen interpretation, and his work will provide both answers for quantum mechanics in the future and maybe consciousness as well in his philosophical dealings.
Thank you, Patrick, for the story. It's admires sometimes what, all these names we read in books and stuff, that they are humans too, and there are a lot of human side to it. Well, thank you for the story. I think we had a great discussion and explanations today. Well, I'll see you guys next week. Take care.
Bye, everyone.
See ya.